Welcome to Chapter 8 of Class 7 Science, Measurement of Time and Motion. In this fascinating chapter, we'll explore how humans have measured time throughout history and understand the science behind motion and speed. We'll meet Prema, a talented runner who dreams of representing India in international sprints. She wonders how time is measured so precisely in Olympic races compared to her school's stopwatch. Through hands-on activities and historical exploration, we'll discover ancient time measurement devices, learn to make a simple water clock, understand pendulum science, and master the concepts of speed and motion. Get ready to become time and motion experts. Let's begin our journey with the history of time measurement. Long before modern clocks, humans observed repeating patterns in nature. The rising and setting of the sun defined a day, the phases of the moon defined months, and changing seasons defined years. Ancient civilizations created various devices to measure time within a day. The sundial used the sun's shadow to tell time, working only during daylight. Water clocks measured time by water flow and were used extensively in ancient India, where they were called Ghatika yantra. Hourglasses used flowing sand, and candle clocks used marked candles. Each device used a different method but the same principle, measuring regular, repeating processes. India had advanced time measurement systems mentioned in ancient texts like Arthasastra by Kautilya, and the great astronomer Varahamihira provided accurate expressions for time measurement using shadows. Now let's get hands-on with Activity 8.1 Constructing our own water clock. We'll need a transparent plastic bottle, a drawing pin, water, ink or food coloring, and a watch or timer. First, we cut the bottle into two parts roughly in the middle. Then we make a small hole in the bottle cap using a drawing pin. We place the upper part inverted over the lower half, fill the upper part with colored water, and mark water levels every minute as water drips down. Our water clock is ready. To use it, we pour water back into the top and watch it drip. Each time it reaches a mark, 1 minute has passed. Simple water clocks like this weren't very accurate because water flow rate decreases as the water level drops. This led to the development of more advanced sinking bowl-type water clocks called Ghatika yantra, where a bowl took exactly 24 minutes to fill and sink. These were used extensively until replaced by pendulum clocks in the 19th century. The invention of the pendulum clock in the 17th century revolutionized time measurement. Galileo Galilei discovered pendulum properties when he noticed a swinging lamp in a church took the same time for each swing, regardless of how far it swung. Christian Huygens later invented the pendulum clock in 1656. A simple pendulum consists of a rigid support, a long thread, and a bob metallic ball. In Activity 8.2, we'll set up a pendulum and measure its time period. We tie a bob to one end of a string, fix the other end to a rigid support, gently move the bob sideways and release it, then measure the time for 10 oscillations. The time period is calculated as total time divided by 10. We discover that the time period depends on the length of the pendulum but does not depend on the bob's mass. All pendulums of the same length have the same time period at a location, and this constancy is used in pendulum clocks. Early pendulum clocks could gain or lose 10 seconds per day, while modern atomic clocks lose only 1 second in millions of years. Now let's explore the concept of speed. Imagine watching a 100 meters race. All runners start together, but soon they spread out. How do we decide who is running faster? The simple rule is, the runner who is ahead at any instant is running faster. Someone who covers more distance in the same time has higher speed. Speed is defined as the distance covered by an object in unit time. The formula is speed equals total distance covered divided by total time taken. The SI unit is meter per second, and another common unit is kilometer per hour. Let's work through an example. If Swati's school is 3.6 kilometers from her house and it takes her 15 minutes to reach by bicycle, we calculate the speed is 3.6 kilometers divided by 15 minutes, which converts to 3,600 meters divided by 900 seconds, giving us 4 meters per second. The bicycle moves at 4 meters every second. Speed, distance, and time are closely related. If we know any two, we can find the third. The basic formula is speed equals distance divided by time. From this, we can derive that distance equals speed multiplied by time, and time equals distance divided by speed. Let's practice with examples. If Raghav is going to a city by bus moving at 50 kilometers per hour and it takes 2 hours, the distance is 50 kilometers per hour multiplied by 2 hours, which equals 100 kilometers. If a train travels at 90 kilometers per hour, the time it takes to cover 360 kilometers is 360 kilometers divided by 90 kilometers per hour, which equals 4 hours. Remember to watch your units carefully and convert when necessary. To convert kilometer per hour to meter per second, multiply by 5/18. To convert meter per second to kilometer per hour, multiply by 18/5. Not all motion is the same. Objects can move in uniform motion or non-uniform motion. Uniform motion means equal distances in equal time intervals, with constant speed and straight line path. This is rare in everyday life. Examples include a car on highway with cruise control or a conveyor belt in factory. Non-uniform motion means unequal distances in equal time intervals, with speed changing with time. This is very common in daily life. Examples include vehicles in city traffic, falling objects, roller coaster rides, or athletes running races. In Activity 8.5, we observe different types of motion by dropping a stone, releasing a ball down an inclined plane, observing a bicycle on road, and watching a pendulum swing. We find that most everyday motion is non-uniform. Since most motion is non-uniform, we use average speed to describe it. Average speed equals total distance covered divided by total time taken. For example, if a car travels 60 kilometers in the first hour and 40 kilometers in the second hour, the total distance is 100 kilometers, total time is 2 hours, and average speed is 50 kilometers per hour. Motion is everywhere in nature, from tiny atoms to giant galaxies. Examples include flowing rivers and streams, moving clouds in sky, ocean waves and tides, wind and air currents, Earth's rotation and revolution, and plate tectonics. All these motions can be described using the concepts we've learned. Remember Prema from the beginning. Now she understands that Olympic timing uses advanced electronic systems that evolved from ancient time measurement methods. Her running speed can be calculated using the speed formula, and her motion during race is non-uniform as she starts slow and accelerates. Her average speed equals total distance divided by total time. With this knowledge, Prema can better analyze her performance and improve her timing. Throughout this chapter, we've explored how time has been measured throughout history, learned to construct simple time measuring devices, understood pendulum properties, calculated speed, distance, and time, and distinguished between uniform and non-uniform motion. You're now equipped with valuable knowledge about the fundamental concepts of time and motion that shape our understanding of the physical world.